So today we're going to talk about rotational motion. Specifically, we're mostly going to talk about torque, but we'll also introduce rotational kinetic energy and rotational momentum. So whenever we're thinking about translational motion and we want to figure out what causes acceleration or translational acceleration, generally we think about force, right? Because a force causes acceleration. So what causes angular acceleration? Well, for rotational motion, we have something called torque. And this is our Greek letter tau, and it is equal to I, which is the moment of inertia. We'll talk about that in a minute, times alpha, our angular acceleration. So just like forces cause acceleration in translational motion, torque causes angular acceleration in rotational motion. So there are two ways that we can define and discuss torque. There is the first equation where torque is equal to radius times the force perpendicular. And this is the formula that we use for torque generally when we have objects that are not already in motion, not already accelerating. Think about like a lever, a wrench, a shower faucet. If you're tightening lug bolts on your car, we'll use this radius and force definition of torque. There is this second definition of torque, though, and this is generally used for objects that are already in rotational motion or are going to maintain some sort of angular velocity. And this is the torque is equal to I alpha. So we're going to cover both of these, but the first one we're going to talk about is the first definition, right? Torque is equal to radius times force perpendicular. So this type of torque depends upon three things. First is the magnitude of the force, right? So how large is this force? The second is the angle of the application of the force. And the third is the position of the force. So the radius value is going to be our distance from the location of rotation, right? So you could think about that like as the pivot point to the application of the force. Things like the angle and magnitude are going to impact that force perpendicular. So I like to remember these as MAP, magnitude, angle, and position. All three of these things dictate how large of a torque and also what direction of torque. So torque also has directionality to it. So counterclockwise is going to be the positive direction of torque. And clockwise is going to be the negative direction. So something that really helps me is I don't know about you guys, but whenever I was a kid, we didn't have that fancy faucet handles. You had like the shower handles that you actually had to turn, like they were two knobs. And my parents would always say, righty tighty, lefty loosey. Well, if I turn an object to the left, it's going counterclockwise. I am getting more or a positive water flow. If I go righty tighty, I turn this object to the right, it is going clockwise. That's the negative direction. I am getting less water flow. So righty tighty, lefty loosey kind of helps me remember this. But counterclockwise is positive, clockwise is negative. And the rate of rotation of an object isn't going to change unless the object is acted on by a net torque. So how do we find the balance point, right? So something like a seesaw is a great example of when we would use the tau is equal to r force perpendicular because this object has an obvious radius between the pivot point and the applied force. In this situation, it would be the weight of the two people on this little seesaw teeter-totter. Well, in translational motion, we know that an object is in equilibrium whenever the summation of forces is equal to zero. Same idea happens with torque. An object is going to be in rotational equilibrium whenever the external torque is equal to zero. So to find the balance point, we would use the summation of torque is equal to zero. Now, in my example of the teeter-totter, I'm only considering the forces due to these two people. I'm not considering the weight of the actual board, the totter aspect of the teetering. But what if I have a situation like this, right? I have a person holding their hand out and they're holding a textbook or they're holding some sort of weight. Well, there is some mass due to the weight of this person's arm. And because the radius from the distance of our pivot point, in this case the elbow, matters, I also have to place the weight of the arm at some specific location. And the location where we place the weight, or the force due to gravity, of this person's forearm, is called the center of gravity, right? So when we need to find the total torque due to the forces of gravity acting on an object, the total force of gravity can be considered to act on a single point, and that single point is going to be the center of gravity of this object. So how do I find the center of gravity of an object? Well, let's say I have this big cloud here, and this big cloud is going to rotate about some pivot point where this axis is. One way to approach this is that we could find all of the particles that make up this cloud. We could calculate the distance from that particle to the pivot point and have the weight or the gravitational force for each one of these. But that would be incredibly time consuming. Or we can find one point or one specific location on this blob where the effect on the rotation of the object is the same as the sum of all of its individual parts, meaning we're finding one location where we can place the total mass of this blob that produces the same result as if we were to take a summation of individual parts. And this is called the object center of gravity. So the way that we do this is we find the center of mass, right? So I take all of the masses times their distance, I sum them all up, and then I divide by the total mass of this object. You are not going to have to do that for this class. All of the objects that we will be looking at will have very obvious locations to place the center of mass. So, for example, if we go back to this person's forearm, we're going to assume that the mass distribution is fairly even throughout this entire person's arm. You're just going to place it at the center of the object. So when we consider the motion of an extended object in relationship to some point, like a pivot point, we consider the motion of its center of mass, right? This is the place where we put the total weight or the force due to gravity of the object at that specific location. But what happens when our torques aren't balanced, right? Well, if the torque isn't balanced, this object starts to spin faster or slower, goes to the left, goes to the right. It experiences some sort of rotational acceleration. And just like linear acceleration changes how fast something moves along a line, rotational acceleration changes how fast something spins. So we can derive our equation, torque is equal to I alpha, looking at Newton's second law, and our definition of torque is equal to the radius times the force perpendicular. So I take Newton's second law, F is equal to ma, and I also take torque is equal to the radius times the force perpendicular. I can assume that the force is the same, that this force is being applied completely perpendicular to the object. I'm just going to plug in ma for this force perpendicular. And I get this equation that says torque is equal to the radius times the mass times acceleration. Great. The problem here is that I have two different types of motion contained in the same equation, and that produces a lot of issues for us. Whenever we're thinking about an object that has translational and rotational motion at the same time, we want to pick like one type of motion and convert everything into that one type of motion. So if you remember, we had ways that we can convert velocity into angular velocity, acceleration into angular acceleration. We're going to want to use these here. So I am going to replace my acceleration with r alpha, right? This is one of those conversions. And this gives me an equation of torque is equal to the mass, radius squared, times alpha. Great. Now everything is represented in rotational terms. Now, before we take this any further, we have to talk about something called the moment of inertia. So in translational motion, we have mass, right? And mass is an intrinsic property of an object that doesn't change. And this mass basically determines how hard it's going to be to overcome the inertia, right? So mass dictates how much acceleration we get out of a force. The same thing happens with our moment of inertia. So in rotational motion, instead of mass, we have something called the moment of inertia. And the moment of inertia of a system really depends on how the mass is distributed and the location of the axis of rotation. And I'll give you some examples of that in a second. But most basic idea, the moment of inertia tells us how challenging or how much torque we need to apply to get a specific object to start to have angular acceleration, to get it rotating, right? So there are ways that you can go about calculating the moment of inertia for different systems. I have decided that that's not a good use of your time. I will explicitly give you the rotational inertia or the moment of inertia for different objects. But as an example, when we have a thin, hollow, cylindrical shell or a hoop, our rotational inertia is mr squared. Whenever we have a solid cylinder or a disk, this changes and it's 1/2 mr squared. And this is because the mass, instead of being distributed along the edges evenly from the radius, now it is distributed throughout the radius, right? So we have changed the distribution of mass, meaning that we have changed the moment of inertia. Same thing with a solid sphere is 2/5 mr squared, and a thin, hollow, spherical shell, so like a soccer ball, is 2/3 mr squared. And these are all assuming that we are rotating these objects about the center of the object. If we don't rotate about the center, we would have to calculate the moment of inertia. And I also like this example of spinning a rod along the edge versus spinning it along the center, right? This is the same object, has the same shape, but changing my location of where I am spinning it about changes the rotational inertia, right? So for this thin rod that I'm spinning along the edge, it's 1/3 ml squared, where L is the length of the rod. Whereas if I spin it about the center, it's now 1/12 ml squared. Again, there are ways to calculate this. I do believe the textbook goes into that. I'm not going to make you do that. So, moment of inertia, the most basic definition of the moment of inertia is the summation of masses times their distance from the axis of rotation squared. That's my R, my radius, the distance from the axis of rotation. So it's an interesting quantity, right? Because we can compare the moment of inertia for, this is not a dumbbell, this is a barbell. I say this every single semester. I say, at least, this is a barbell, fix it. But I still have a dumbbell. I will make a note in my brain to fix that, but I probably won't. So I can spin this barbell about the center, or I can spin it about the edge. So if anybody goes to the gym, I assume most people do. That's good. It's good for your health. It's good to, keep you sane and stuff like that. Imagine if you were to pick up a barbell and try to spin it about the center versus if you were to try to pick it up at the edge where the plates are and spin it that way, right? Conceptually, anybody that has lifted weights can say, oh, well, if I pick it up from the center, that is going to be significantly easier to spin it than if I pick it up from the edge. Why is that? These things have the exact same total mass. They're the exact same size, but all I did was I changed the location about which I am spinning this. Well, if I calculate the moment of inertia, we can see that it's going to be different for these two. So if I spin it about the center, my moment of inertia is 2mr squared. Whereas if I spin it about the edge, my moment of inertia is 4mr squared. And this has to do with the fact that the torque that is being applied from this mass has a significantly longer distance or radius away from my axis of rotation. So this is a great example, I think. Sorry, that's my dog. This is a great example, I think, of how changing where you rotate an object changes how hard it is going to be to get this object to rotate. So, if an object consists of a small number of particles, we can calculate the moment of inertia directly. But for symmetrical objects and everything that we look at in this class, there's going to be a table. It will be provided on the exams. You're not going to have to calculate it. So what I want to do is I want to take this mr squared and I want to replace it with the moment of inertia. So the most basic definition of the moment of inertia is the summation of masses times the radius squared. So I can just replace this mr squared with I, my moment of inertia, and I have our second definition of torque, where torque is equal to my moment of inertia times my angular acceleration. And so we'll see that applied in things like yo-yos, right? So I can use F is equal to ma to arrive at this following equation for torque. Now, if I have a yo-yo, I would want to think about something like what is causing the rotation. In this case, it is the tension from the string. You also have the mass pulling down. And in these types of problems, we will need to look at both types of torque. We will need to look at torque is equal to R times F, because that F is what's causing the rotation. And we will also need to look at torque is equal to I alpha, because the alpha is the angular acceleration. Remember that torque is torque. We can set these two equations, these two definitions of torque equal to each other. And I'll go through some examples of this in class. So if we can have work done by forces, we can have work done by torque, right? So work done by torque is equal to the forces applied times the arc length, right? So the arc length of the object's rotation. I can state that torque is equal to R times the force perpendicular, and arc length is equal to R times my change in angle, right? My change in theta. So work is equal to torque divided by radius times the radius, change in theta. Simplified, work is equal to torque times delta theta, my change in angle. Remember that power is work done over some change in time. So if I divide my work by a change in time, I get that power is equal to torque times my angular acceleration, omega. This means that we also have definitions for rotational kinetic energy, right? So just like we had translational kinetic energy, now we have rotational kinetic energy. So rotational kinetic energy is 1/2 I omega squared, where omega is your angular acceleration, I is your moment of inertia. So we can derive that from just standard representations of kinetic energy, right? 1/2 mv squared. So I want to change my translational variables into rotational variables. I want to replace my v with r omega. So I have to square both of those, which gives me 1/2 mass radius squared omega squared. Remember, mr squared is my most basic definition of my moment of inertia. Kinetic energy of rotational motion is 1/2 I omega squared. So for systems that have both translational and rotational motion, like a ball rolling down an inclined plane, we have to include both types of kinetic energy in our conservation of energy equations. So this would be applicable to something like the motion of a car tire. It is translating and it is rotating. The rolling of a ball, because this ball is translating and it is rotating, we have to include both types of kinetic energy. In translational motion, we had momentum and the conservation of momentum. Well, in rotational motion, we also have angular momentum and the conservation of angular momentum. So I can start with my definition of torque is equal to the moment of inertia times alpha. And alpha is my change in angular acceleration divided by a change in time. I can plug this in, and we can define angular momentum as this L. Why it's an L, I don't know, but it is the letter L, is equal to I omega. So our torque is equal to a change in angular momentum divided by a change in time. This is very similar to whenever we had force is equal to a change in linear momentum divided by a change in time. See, there are a lot of parallels here in physics. We are changing variables, but the concept itself is still similar. And because we have a conservation of angular momentum, we state that the summation of the angular momentum initial has to be equal to the summation of the angular momentum final. A great example of this is whenever you have like an ice skater and they're spinning in a circle, whenever they pull their arms in, they start to spin faster. They have changed their distribution of mass, but they have maintained their momentum. And we'll do an example of this in class.